In August 2024, the X-ray observatory XRISM aimed at a faint galaxy merger and found its center under extraordinary strain. Stars were still forming across the system, yet the central supermassive black hole was feeding hard, and its X-rays carried the signatures of several winds moving at enormous speed. That is the contradiction. One galaxy is busy building stars while its center may be gathering enough influence to change their future. What woke this black hole and why now? How can a spectrum reveal an invisible wind moving faster than anything we can see directly? Could the same sequence ever reach the center of our own galaxy and reshape the gas around it? Black holes don't come with indicator lights, so waking is an interpretation, not a recorded instant when darkness became activity. The merger appears to occupy a short evolutionary stage in which the starburst is still raging, while the nucleus becomes intensely active. For now, don't chase the wind, follow the gas. The first clue begins far outside the black hole, in the wreckage of two galaxies pulling each other apart. To reach the answer, we have to follow the matter. First through a collision between galaxies, then into a crowded galactic center, and finally into the narrow X-ray fingerprints left by iron stripped almost bare of electrons. Along the way, one apparently simple story will split into two: what the merger may have done, and what XRISM actually measured. Keep those separate, because the most interesting part of this discovery lives exactly on that boundary, and the final wind speeds won't make sense until both halves are in place. Start with scale. At the center of the Milky Way sits Sagittarius, a star, a black hole of roughly 4 million suns. Yet the cosmic horseshoe gravitational lens may hold a central black hole near 36 billion solar masses, a model-based result, not an uncontested largest ever trophy. At that scale, you'd expect mass to do the talking. It doesn't. A black hole becomes conspicuous when surrounding matter falls inward, heats up, and releases energy before crossing the point of no return. Without that bright material, even a gigantic black hole can hide in plain sight, betrayed mainly by its gravity. Sagittarius, a star, is our nearby example of a relatively quiet center. The object inside IRAS 05189 2524 is the opposite kind of scene: a dusty merger, an active nucleus, and signs of rapid feeding happening together. That changes the question. We're not trying to prove that this black hole had never been active before, because older X-ray observations already show that it was. We are trying to understand why activity is intensifying during this stage of the merger, how the feeding connects to the winds, and whether those winds have enough influence to change what the galaxy becomes. The first clue is not inside the black hole. It is spread across the wreckage around it. A galaxy merger is less like two solid objects crashing and more like two gravitational systems pulling each other apart while passing through. Their stars are usually separated by enormous distances. Their gas is not so aloof. As the galaxies interact, gravity stretches their shapes and disturbs great reservoirs of gas and dust. Clouds are compressed, dense regions collapse, and new stars ignite across a system already changing shape, producing the intense star-forming state astronomers call a starburst. That is one possible outcome of the disturbance, not a rule for every merger. Current simulations do not support a simple conveyor belt in which every major merger automatically produces a quasar, shuts down star formation, and leaves an elliptical galaxy behind. Many galaxies grow and quiet through other routes. But IRAS 05189 2524 is a particularly revealing case because several stages overlap in one place. It is a late-stage merger. It is an ultraluminous infrared galaxy. It contains a starburst and an active galactic nucleus at the same time. Keep following the gas and the route divides. Some collapses into stars, while the changing gravitational landscape pushes some onto a very different journey, gradually exchanging wide galactic orbits for a crowded path toward the central engine. Some disturbed gas collapses far from the center and helps build stars. Gas that loses enough orbital momentum moves inward instead. In this system, the merger offers a plausible path toward the nucleus, where the destination is the bright flow around a supermassive black hole. One disturbance may be stalking both sides of the conflict. Same raw material, opposite destinations. Before we follow that gas all the way in, switch eyes with me. Visible light gives us stars and structure, but this merger is wrapped in material that makes infrared and X-ray observations especially useful. Infrared tells us that enormous energy is being processed through the dusty system. X-rays lead us toward the compact, violent region around the active nucleus. That is why the target's history is spread across observatories. The infrared astronomical satellite cataloged it in 1983. Decades later, XMM Newton and New Star found an active nucleus and a fast wind. Then XRISM arrived with a much sharper way to separate X-ray energies. Think of the observations as layers rather than competing pictures. Infrared shows the dusty star-forming environment. Broad X-ray coverage reveals the energetic nucleus. High-resolution spectroscopy breaks its light into features fine enough to measure motion. The galaxy isn't changing between those views, our evidence is. The black hole itself remains dark. What changes from layer to layer is the evidence left by matter before it disappears, and by matter that gets thrown back out. Follow the inward branch, and the gas doesn't simply drop straight through. It gathers into an accretion flow, where collisions and compression make it radiate intensely. A feeding black hole can turn a tiny galactic center into an active galactic nucleus. As feeding intensifies, radiation pushes outward and magnetic fields may redirect charged material. Researchers still debate the balance of launch mechanisms in systems like this one. XRISM didn't settle that question. What it did see was the result: highly ionized winds leaving the black hole's vicinity at substantial fractions of light speed. Ultrafast outflow is the technical name, and here it means several streams moving toward us at different velocities. Extend XRISM's wide-field X-ray imager recorded a broad spectrum and rapid variability, likely associated with near-Eddington accretion. The nucleus appears to be feeding near a theoretical limit where radiation pushes strongly back against further inflow, so the black hole's bright surroundings are effectively resisting the same supply of matter that keeps them luminous. That gives us the first half of the engine, intense feeding near the center. The second half is what escapes, and what it encounters on the way out. Now the story reverses direction. The gas fell inward, energy comes back out. Extend those winds beyond the accretion flow, and they meet colder molecular gas, the raw material for future stars. If a nuclear wind transfers enough energy and momentum into it, dense clouds can become harder to maintain. Star formation could then decline, but only if energy from the compact nucleus couples efficiently to gas spread across the much larger galaxy. In the proposed life cycle, the merger helps create a starburst and feed the nucleus. Strong outflows may later suppress the same star formation that surrounded their rise. The researchers place this object in a short-lived phase likely preceding a quasar. It's an elegant loop. Disturbance supplies fuel, fuel drives activity, and activity may remove access to fuel. But the universe doesn't owe us a tidy sequence. Simulations show that mergers are neither necessary nor sufficient for quenching galaxies in general. Has any one system shown the critical pieces together clearly enough to separate observation from a convincing cartoon? This is where the neat story becomes an evidence problem. IRAS 05189 2524 wasn't a newly discovered active galaxy. Earlier X-ray observations had found an active Seyfert nucleus and evidence for one ultrafast wind near 11% of light speed. They didn't reveal the more complicated structure hiding inside the iron features. XRISM was built for this separation. The JAXA-led mission launched on September 6, 2023 with NASA and ES a participation and remains active. Its instruments divide the labor. Extend is a broad-field X-ray imager, while Resolve is a microcalorimeter spectrometer in which each arriving X-ray causes a minute temperature rise, letting the detector measure that photon's energy precisely. During XRISM's performance verification phase, when early observations were testing and demonstrating what the mission could do, the team pointed both instruments at the merger in August 2024. The goal wasn't to photograph a black hole switching on. It was to read the energetic material around it closely enough to ask whether the earlier single wind picture had been hiding several components. Now the problem had become measurable. First, though, the target itself had to earn its place in the story. IRAS 05189 2524 begins with the mission that cataloged it, the infrared astronomical satellite, launched in 1983 for the first space-based infrared sky survey. Its prefix marks how the system entered the story, through heat-associated light, not the crisp visible outline of an ordinary spiral. This target is an ultraluminous infrared galaxy and an X-ray bright late-stage merger, where intense star formation and an active galactic nucleus coexist. That combination makes the target useful, because infrared establishes the dusty starburst environment, X-rays expose activity near the black hole, and the merger places both inside a system undergoing violent rearrangement. No label proves a life cycle, but together they identify the junction the theory cares about. Stars are still forming, while the nucleus is already throwing energy into its surroundings. Earlier observations had already shown an active nucleus. A later new star XMM Newton analysis reported a blue-shifted iron feature consistent with an outflow around 11% of light speed, although related features weren't all statistically strong. So XRISM wasn't arriving before everyone else. It was arriving with a better ruler, able to ask whether one broad absorption clue was really several narrow motions crowded together. The team interpreted the galaxy as a short-lived stage after a major merger, during an intense starburst and likely before a quasar phase. That's an interpretation, not a timestamp. Its value is the overlap of fast feeding active star formation, and wind. Resolve could test whether the older spectrum's apparent single component was simple or blurred together. If blurred, the iron absorption would split, and each shift would carry a velocity. And that is why the answer is hidden in a part of the spectrum most viewers never have reason to think about. A spectrum sorts arriving light by energy. Peaks mean extra X-rays, dips mean intervening material absorbed particular energies. Instead of seeing the wind directly, you see the precise places where it has taken bites from the source's light, like a missing tooth pattern whose spacing carries information. Near an active black hole, radiation can strip most electrons from iron. Helium-like and hydrogen-like iron, names describing the remaining electrons, leave absorption fingerprints near 6.7 and 7.0 kiloelectronvolts. Those known rest energies give astronomers reference marks before any motion shifts the pattern. Now put those ions in a wind moving toward us. The familiar effect is redshift. A receding source's wavelengths stretch toward red. Motion toward us compresses them toward blue. Andromeda is a nearby example because it approaches the Milky Way, although uncertainty in its sideways motion makes any eventual encounter less certain than older headlines suggested. X-rays aren't visible blue light, but the Doppler logic holds. An iron feature appears at higher energy when the absorbing wind races toward us. Account for the galaxy's own redshift, compare the observed feature with the iron reference energy, and the amount of displacement becomes a speedometer for material no camera could track across the frame. One complication remains. A single velocity wind should make a relatively simple feature, while separate regions moving at different speeds can leave several. Limited energy resolution blends neighboring signals, sharper resolution can divide them. Once you see that, the graph stops looking like static and starts looking like traffic. Resolve found an unusually complex rest frame spectrum between roughly 7 and 9 kiloelectronvolts. The team interpreted it as highly ionized iron absorption from multiple ultrafast outflows, plus a broad iron emission feature. Notice what happened to the mystery. The black hole woke up became a measurable chain. Outflowing iron removes specific X-ray energies, those energies shift, and each shift reveals motion toward us. The state change isn't one magic frame. It's an interpretation built from feeding, variability, and spectral structure earlier observations couldn't cleanly separate. So how many components were hiding there? We followed gas inward. XRISM caught what came back out. Resolve separated at least 3 bulk velocities. The components moved at roughly 7.6, 10.1, and 14.3% of light speed. The fastest covered more than 40,000 kilometers each second. These aren't photographs of objects leaving a black hole. They're modeled velocity components encoded in shifted iron absorption, all moving toward us. Earlier work indicated one wind near 0.11 times light speed. XRISM's sharper spectrum exposed several outflowing regions instead. That is the observation the headline has to protect. Not the first hint of activity, but a newly resolved view of a far more structured wind system. Extend recorded broadband behavior and rapid variability, likely tied to Near-Eddington accretion, while Resolve separated the winds. Intense feeding and multiple outflows occupied the same late-stage merger. The estimated wind energy exceeded that of the galaxy's slower molecular outflow. JAXA reports more than 100 times greater. Researchers consider that sufficient in principle to suppress the starburst. In principle, matters because nuclear energy must couple to galaxy-scale gas before star formation changes. XRISM didn't watch that finish. It measured an engine powerful enough to make the consequence credible. That's the real awakening, a detailed view of a rapidly feeding nucleus pushing against its galactic environment. Together, the pieces make a strong case for black hole feedback during a merger. Active star formation, rapid feeding, multiple ultrafast winds, and enough estimated energy to influence star-forming gas. It doesn't prove every merger follows this path or that these winds have quenched this galaxy. Researchers still need to learn how the components vary, where they form, and how efficiently their energy reaches colder gas. Future observatories could compare many systems at different stages. ESA's new Athena is in study, with adoption proposed for 2027 and launch planned for 2039. Its proposed X-ray integral field unit and wide field imager would examine matter and energy moving around black holes with greater reach. XRISM has given astronomers a sharper frame in the sequence. New Athena may help turn frames like this into a population-level story, testing inflows and outflows across many black holes instead of treating one merger as a universal template. Now return to Andromeda, where the familiar forecast said the approaching galaxy and the Milky Way would merge in roughly 5 billion years. Newer Gaia and Hubble-based modeling makes that far less certain. With the major local group galaxies included, there's close to a 50% chance of no merger during the next 10 billion years. That's no guarantee either way, because the future orbit depends on motions, masses, and neighboring galaxies we don't know perfectly. A cosmic forecast is not an appointment card. Suppose it happens. Gravity could compress gas into new stars and send some toward the galactic centers. Sagittarius A star might feed more intensely, and winds from a brighter nucleus could interact with the remnant's gas. Every step is conditional because mergers don't always trigger strong accretion. Accretion doesn't always produce the same winds, and powerful winds don't automatically shut down a galaxy. That's why the XRISM target matters. It isn't a Milky Way prophecy. It's a real system where the ingredients overlap: merger, starburst, rapidly feeding black hole, and several winds energetic enough to matter. Our galaxy's future remains unwritten, but the physics shaping one possible version has become easier to read. One distant merger turned an invisible process into something measurable: three iron signatures, three wind speeds, and one black hole feeding near its limit while stars are still forming around it. That's the useful part of a discovery like this. The strange headline becomes a mechanism you can actually follow. If you like explanations that follow the evidence all the way from a strange headline to the mechanism underneath it, subscribe to Oddly Useful Dude. The next useful surprise is usually hiding in a system everyone else walked past.